Hello. So welcome today with another episode on crystallography. So we are again going to start with some residual concepts in crystallography. Okay. So crystallography. What we discussed last time, we need to uh, recap a little bit. So what we discussed is about what is structure factor, and we also discussed about different geometry like FCC, BCC, or simple cubic. These can give rise to some forbidden peaks because of the nature or the mathematical equation of the structure factor. So we discovered that the structure factor for a BCC lattice would look like e to the power I pi into HKL, H plus K plus L, where HKL are the Miller indices of the lattice plane. For FCC, we found out that this was the structure factor. So here, for constructive interference, the condition was H plus K plus L must be even. And for this, mathematically, we can see that this can be HK even, L odd, or HK odd, L even. So there can be two kind of possibilities here. So if H and K both are even, then these are going to give you 0. So H, K and L, everything has to be odd or everything has to be even. So everything is even or everything is odd. So that is the only possibility here. So that being said, so another very interesting exercise would be to do and to find out what is a diamond structure and to actually see what can be the forbidden planes of a diamond structure and what will be the formula of the structure factored there. So now what we kind of assumed that each, so again you might have to kind of look back into the earlier lecture, but what we assumed was that, let's say there are two atoms in two planes and there is a light ray coming in and there is a light ray coming out, and each of this and this A and B have equal intensities for the light rays coming out. So that is something we assumed. So that's why we added the phases up. We said that okay, it is like the phase e to the power I pi in sorry e to the power I theta of A plus e to the power I theta of B, where theta of A is the phase which the light gets from traveling through the point A. Let's say this is the source, this is the maybe the screen, or maybe some other point, let's say O. So theta A is the phase the light gets by passing through SAO, and theta B is SBO, passing through SBO. So we are kind of assuming that e to the power this and this will have the same amplitude, because this and this will have it will kind of it will kind of diffract the light in a same way, but that might not be true, and in reality what happens is that is not true. So what happens is why does the atom why does an individual atom actually diffract? That's again because it's the same thing, it's because of the electrons. So let's say there is an atom and there is a nucleus which is positive and there is an electron cloud. When X-ray comes, a photon comes, then a photon collides with some electrons. So let's say the photon comes, photon is a particle, and it collides with some electron. So now we are thinking everything as a particle, but obviously in quantum mechanics, nothing is a particle, everything is a wave. But for analogy purposes, we can still think of them as particles. So what happens is the electron goes, collides with the photon. So the X-ray comes, so it's an elastic scattering. What happens is it just changes the it just changes the direction, right? So the photon changes the direction, and that's why we are having this kind of diffraction. Again, the X-ray, the direction will be all, so it will not only be theta 1 equals to theta 2. It's like not like the reflection thing that we saw, right? In every Bragg's law, in everything. So in Bragg's law, let's say this is Bragg's law, we saw that the light was reflecting, right? So theta 1 will be equal to theta 2. That is what we saw in Bragg's law. But that is not the case. That only happens because if theta 2 is not equal to theta 1, and this is also a light, so the blue light, so I'm drawing it with blue line. So the blue light and the green light, they will not constructively interfere for any angle of theta, so it can be mathematically proven. I think so we have also discussed it about in the late earlier videos that theta 1 has to be equal to theta 2 so that there is a constructive interference between the green light and the blue light. So that being said, what we can actually do is um, okay, so same thing happens for electrons, because electrons, there is not only one electron, right? So there are multiple number of electrons. There are multiple electrons, and when they will also interact with each other, this light and this light will also interact with each other to give rise to some diffraction patterns. And this is where there will be another structure factor included in the atom itself, because the structure factor, we saw that it comes because there are different particles at different places, and the light diffracts from each of them and they interfere, and that's why we get this structure factor thing. So each atom, because it has, like, atom is not a single particle, but it has all these electrons and the nucleus, so all of this will constitute another structure factor, but this is called the form factor of an atom. This is called the form factor of an atom. So just like what we did is, for example, there is an electron here, there is an electron here, and in quantum mechanical sense, the let's say the probability of the electron being here is rho of r a. This is point A. This is rho of r b, point B. So this, the net result of this will be rho of r a e to the power I theta a plus rho of rb e to the power I theta b. So yeah, it will be the structure factor. So now the thing is, if we integrate it all over the space, so what we will get is, yeah, so we can also take some phase out to get rho ra e to the power I ra plus rho rb e to the power I rb, right? So just like we did in the last video. And now for generalizing the whole atom, we can actually get the structure factor to be e to the power rho of r e to the power, uh, okay, so there is a missing g, yeah, e to the power g dot r dr. So this is the form factor. So just we converted this summation to an integral because rho is now, like, rho is present everywhere. Rho is present everywhere in the space. So this is called this is, I am writing it by f, not s. This is called the form factor. So what will happen is, actually, if there are the form factor of different atoms are different. It solely depends on which atom it is and what is the charge of that atom. Let's say the CS, cesium, and cesium plus will have different form factors, and also the form factor depends on the theta angle, because you can see that it depends on g, and g is actually theta. G represents theta, that which, what is the theta by which you are, someone is shining the light. So it's kind of like the Fourier transform, the g vector component of the Fourier transform of the electron density. Okay, so that's why you'll see that, for example, in an FCC lattice, there are four different atoms A, B, C, D, which are occupying the basis, the lattice basis, Yeah, so let's say at 0 0 0 it's A, at half 0 0 it's B, at 0 half 0 it's C, at 0 0 half it's D. So there are four different kind of atom. It's rare, it will not happen, but let's assume. So actually the structure factor is not given as the formula above, but it is rather given as Fa plus Fb e to the power k plus L plus Fc e to the power h plus L plus Fd e to the power h plus k. So you can see that the prefactors or the amplitudes will be different. That's why what you will see is even the forbidden peaks, if the atoms of the FCC lattice or a BCC lattice or a diamond lattice, they're different from each other, they have different form factors, you will see that the forbidden peaks will reappear, because even if the phases are destructively interfering, because of the different amplitude they don't cancel each other exactly. So it can be Fa minus Fb plus Fc minus Fd, for example, for destructive interference. If all of these Fs were equal, then it will become zero. But now it is not, because A, B, C, D, they are different atoms. So these are called superlattice reflections. So these are called superlattice reflections. You can study about this in gallium arsenide, or like there are many atoms which have many, like NaCl, they have different atoms, right? CSCl, they have different atoms, and you can see that there will be weak superlattice reflections also present with the normal reflection, so the forbidden peaks will reappear. So that concludes our discussion about form factor and structure factor, and next time we will start with Drude model and the electron models in the solid state, and from the Drude model we will gradually incorporate the concept of reciprocal lattice vectors into our studies, and we will see Sommerfeld models, and we will see electrons in a weak potential and all those things, and by that we will gradually build it up. So this, all of this crystallography thing actually existed, and in the course, to give you a flavor of the relevance of reciprocal lattice vectors in practical studies, or practical crystallographic or experimental studies. So see you in next class. Thank you. Best of luck.